So our next lab, determining the Ka for aspirin. So this lab is actually going to take a little while. It's going to be a 3-part lab, and what we're going to start with is standardizing our NaOH solution. We're going to use NaOH to determine the Ka of aspirin, and the first step is to ensure that the concentration of the base, the NaOH, is very precise and correctly established to begin with, because that's what we're going to base our results on, is the concentration of the base. So we're going to do that, standardizing the base using KHP, which is potassium hydrogen phthalate. And the reason why we're going to use that is because it's an actual solid. And so we're going to start by measuring 0.5 grams ish of KHP, and we're going to carefully record the exact mass. So 0.5364 grams of KHP. So we've carefully measured the KHP, and what we're going to do is we're going to add the KHP to some water, and we're going to make a solution. And we're going to carefully add all of the KHP to the Erlenmeyer flask. And we're going to rinse the watch glass with a little bit of water and pour that into the flask, just to make sure that we get all of the KHP. Add some water. And the amount of water that we add doesn't really matter, because adding water doesn't really change the amount. Well, it doesn't change the amount of acid that we have into the Erlenmeyer, right? So when we're titrating and we get to the equivalence point, we're going to get the moles of acid, which will be equal to the moles of base. And so therefore, adding a little bit more or a little bit less water doesn't change anything. We're going to put in a few drops of phenolphthalein indicator, and phenolphthalein will change color between 8 and 10. And since we're titrating a weak acid with a strong base, our equivalence point will be basic. So phenolphthalein is a good choice of indicator for that. Our burette is loaded with the NaOH, and so what we're going to do is we're going to titrate to the end point. Hopefully we'll get it to 1 drop of a color change. So as we titrate, we swirl the flask continuously. It helps to have a white piece of paper underneath as white background, which we're not being too careful with the NaOH at this point, because it's really not changing color. Now it's starting, we see some pink appearing. So we're going to decrease the flow of NaOH as it seems like we're getting closer. So now we have a drop by drop pink is lingering a little bit more, so we must be getting closer still. You probably can't see this in the video, but at this point it is just, we have it, I have it dropping, drop, 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 drop into the solution. I want to know exactly what the one drop that's going to create a permanent color change. We're very close. And I think we have it. Just went away, so one more drop. One more. There we have it. Now we have to read the volume of NaOH that we used to get to the endpoint. So now that we have the volume of NaOH used, we can calculate the exact concentration of the NaOH, because we know that where we at using 27.20 milliliters of base, we are where the moles of acid are equal to the moles of base. So we can calculate the moles of acid from the mass of KHP, because the mass divided by the molar mass is going to give us the number of moles. And so the mass is 0.5361 grams, and the molar mass is 204.23 grams per mole. And so therefore that's going to give us our number of moles, which is 0.002625. And so those are moles of KHP, which at the same time they're the moles of NaOH, because the moles of acid are equal to the moles of base. So therefore we can get the moles of NaOH divided by the liters of NaOH that we used, and that's going to give us the concentration. So we could use 0.002625 moles divided by, and since we use 27.2 milliliters, in liters it's 0.0272 liters. So we're at 0.0965 molar. And we expected it to be 0.1, so we're pretty close. Now that we have the concentration of NaOH, we can find the Ka of aspirin. So we're going to reload the burette and measure a little bit of aspirin and make a solution. So now that we have a standardized NaOH solution, we're going to go ahead and make the titration curve. And to do that, we need to measure 0.36 grams of aspirin. And then we're going to dissolve that in 95% ethanol. So first step, 0.36 grams of aspirin.
Well, no, you know that you trap. Oh, 20 grams. Yes. Then that would be Alright, Pretty sure other people have touched their So it actually lost?
And 0.3613. So we're going to make our solution of aspirin, and we're going to take our sample of aspirin, and we're going to mix it with 95% ethanol. So we have 10 milliliters of 95% ethanol. Dissolves very, very quickly. We're going to add 50 milliliters or so of water. And now we're going to make a titration curve, and so we're going to add our NaOH, and we're going to add 2 milliliters at a time until we get to about 20 milliliters used, and then we'll switch to half a milliliter at a time until we get to the end point. And once the end point has been reached, which we will know because there will be a spike in pH, and our pH is going to go probably around 9.5 or 10. So once we get there, then we're going to resume adding the NaOH at 2 milliliters at a time until we've added about 38 milliliters or so, just to complete our graph. So we have calibrated our pH meter, and we are starting our titration curve at the pH of 2.11, and we are adding 2 milliliters of NaOH at a time.
You guys redo it? We're just doing our
2 milliliters added.
There's still more in it.
Yeah, I know.
More water.
I'm just I'm waiting for a second.
More water.
And we're at 2.19.
Yeah. More water. There you stop affecting it. More water. Water for days. It's just a prank, bro.
2.29, and we're going to continue like this until the first 20 milliliters are added. So after 20 milliliters added, our pH is at 3.4. We're going to continue now adding 0.5 milliliters at a time. So after adding 26.5 milliliters of the NaOH, our pH jumped to 8 from 5.36 to 8, and then after adding 27.5 milliliters, our pH is now at 10.18. So now that we've reached over 10, we're going to proceed with 2 more milliliters at a time. All right, we got this done. We added NaOH, and so in Excel, we're going to graph our data in Excel. We're going to make one column for the volume of NaOH that we added, and then another column for the pH of the solution. When we do a graph of this, we're going to get something like that, which we're going to use to identify first the equivalence point. So the equivalence point, when you look at your graph, there's going to be a steep part, and up halfway up the steep slope is the equivalence point. So for me it was easy because I had a point right there halfway up. For you it may not be so obvious. So what you need to do is to take the steep part of the graph, and then halfway up, that's your equivalence point, where the moles of acid are equal to the moles of base. So if you go down to the volume of NaOH, in my case, I added 27 milliliters to get to the equivalence point. So 27 milliliters is the volume of NaOH that I added. So in this case, in this activity, we're trying to find the Ka. And to find the Ka, we actually need the pKa. And the pKa is the pH at the halfway point, so at the half equivalence point. So in my case, I had 27 milliliters of NaOH at the equivalence point. So the half equivalence point is at 13.5 milliliters, so half of 27. So this is the half equivalence point. So what I have to do now is to find the pH at the half equivalence point. So if I go up to my line and then find the corresponding pH on the y-axis, so this value will be the pH at the half equivalence point. So for me, it's about 2.85. So 2.85 being the pH at the half equivalence point is the pKa of salicylic acid, determined experimentally. So for me, the value of the pKa would be 2.85. So once you have the pKa, then all you have left to do to find the Ka is to take 10 to the negative pKa, so 10 to the power negative 2.85, and that would give me my Ka value. All that's left to do is to calculate your percent error from your pKa compared to the actual pKa of salicylic acid, which you can easily find online. So I wish you luck, and hopefully you did well on this lab.